professor in the Department of Statistics at UC Riverside. He received his doctorate in biostatistics from University of Michigan, Ann Arbor. Before he moved to UC Riverside, which was just this year, he was actually, for 3 years, he was at UCLA, yeah. So for 3 years before moving to Riverside. His research focuses on high-dimensional statistics and modeling, as well as machine learning methods for imaging data. He also has a wide range of interests in survival analysis, longitudinal data analysis, and application in genetics, epidemiology, in medical problems. So without any further ado, Dr. Faye, again, thank you so much for this opportunity. It's all yours now. Thank you.
Yeah, thanks, John. And good morning, everyone. It's my pleasure to have this opportunity to introduce some of the machine learning or statistical learning methods to this group audience. And I think to get started, I would love to get some of your background. Maybe an easy way for me to know your background is if you could type in the chat what's your scientific field that you work in, and if you have any how would you describe your statistical knowledge? For example, for example, let's say none, some, or expert, right? Let's just say to make it simple, 3 levels. So I could get a better sense of the group we are gonna go over, right? So in some sense, this machine learning and statistical learning, it is involves some statistical knowledge. So I will try to explain things as clear as possible. And yeah, if that makes sense. So for everyone who's here, if you could, type your research field or the field that you work in the chat box, I would really appreciate it. So I see, yeah, thanks, sweetie. Molecular biosciences and bioengineering, computer science education. That's very good. Yeah. Yeah, I would consider, those fields are closely related to statistics. Yes, thank you very much. Jennifer, pharmaceutical science. Yeah, thank you. So I will get started, sharing my lecture notes. Let's see here. Okay, so actually I will be, you'll be stuck with me for the next 2 weeks, not just 1 week. Whether you think this is, good or bad, I guess we'll find out at the end of the course. So for this week, so the title may not be informative, since I just put machine learning and predictive models 1 and 2 for the title. Yeah, thanks. So I see some more responses. Farmer metrics, mixed effects modeling, and public health. Yeah, so I was in the BioStat department, under School of Public Health. So yeah, I think it's the most relevant. Thanks all. So we could, go back to some of the descriptions of the 2 modules to give kind of an overview of what I'm going to talk about, right? So for the first module, I will start with predictive models for high-dimensional data. So these high-dimensional data we consider them, they are everywhere in today's research, especially, data related, right? Data science research. We could see a lot of high dimensional data, for examples, in genetics, epigenetics, and other biomedical data, right? We will, go into like the formal definition. What do we mean by high dimensional data, and what kind of models people have developed and widely used regarding predictive models, right? So here, the keyword is also predictive, meaning that, we are interested in a certain outcome, right? Or people call them response variables of interest. And we want to use the models for prediction or statistical inference, right? And we will start with, some introduction, the fundamentals of statistical learning, and then we will talk about linear models, right? So everything starts with linear models. I think that would be a good starting point. And then for high dimensional modeling, there are a lot of techniques we want to cover, for model selection. So including subset selection, shrinkage methods, or many more that we will cover. So another important topic is that we will introduce, resampling methods. Resampling is one of the fundamental techniques in statistics that, as statisticians, we might have, used them very frequently, but introduce this resampling methods to a larger audience would be, I think, beneficial to the progress of the field, different fields as well, right? So resampling methods, and then we will further introduce, some model inference methods based on resampling as well. So to summarize, the first week, we will be focusing on these predictive models. And then for the second week, one thing we want to, advance based on the first week's material is we want to, extend our knowledge to nonlinear models, right? So as we know, linear models, they are very powerful. They share the simplicity, and interpretability of the model results. However, in modern machine learning methods, as some of you might have heard, the words of like deep learning, deep neural networks, or reinforcement learning, and also all types of machine learning terms, right? And the majority of those machine learning methods, they are nonlinear methods. So it is important for us to, understand the difference between linear methods and the nonlinear methods. So we will move on to nonlinear methods for the second week. So these nonlinear methods, start with nonlinear univariate techniques, right? So by univariate, meaning that, we only have one predictor, right? And so there are specific models that deal with just one predictor, and they are the, the foundations for us to work with more complicated nonlinear models, right? So including, kernel smoothing and splines, that's what we are going to introduce. Then we will, introduce more advanced models, including neural networks, random forest, support vector machines, right? All of those machine learning methods, see, how they compare, what's the difference, which one might have advantage over others in certain conditions, in certain situations, right? So So that's, like a brief overview of what we are gonna cover. Hopefully that gives you a sense of, what's ahead of us. Yeah, also, by the way, I would always welcome, any questions that you have. So feel free to interrupt me during the talk, right? Any questions so far, feel free to speak up. If not, we will, go start with the introduction. So first, to start with, actually, so the majority of these lecture notes, they are based on one course that I have been teaching in recent years. And so this course is, the Statistical Learning Methods course. And a lot of the materials, they are also based on these textbooks, right? So there are two textbooks that I listed here. The first one is Elements of Statistical Learning, the ESL book for short, right? And the second one is Introduction to Statistical Learning. So as suggested by the book title, actually, you could see that ESL is essentially, the more comprehensive book on statistical learning. And then ISL is kind of like a more introductory book, but it tries to grab the essence from the ESL book. So both are very good books that covers the major fields in statistical learning, gives a very detailed statistical background and the derivations to all kinds of methods. So another good thing is that both books have free online versions that you can get easy access to. So if you want to look into more details of some of the topics, right, that we cover in this lecture, you feel free to find these two books, and you can definitely get some detailed knowledge from the materials in these books. Okay, so so we will encounter some data application as well as coding, right, in these two modules. So mostly they are based on R, and as you might know, currently in the statistics community, R may be still the most widely used programming language so far, but I'm also aware that Python is catching up very quickly, mainly because of Python's better capability of fitting machine learning or deep learning specifically, right? So deep learning models. So when we move on to introduce neural networks or other deep learning methods, we will talk about Python coding. But for the majority of the course materials, R would be sufficient, and R is actually more appropriate to carry out most of the methods that we will introduce here. So if you are not familiar with R, oh, by the way, I believe I will upload these lecture notes to your GitHub repo, right, repository, and it will be available to everyone. And so there are some hyperlinks in the lecture notes you could check out later as well. So yeah, even without using this online R tutorial, the link here, you should be easily find online resources that give you introduction to R or related R topics, right? So R and Python, mostly R will be using for this, for the 2 modules. So before even we get started, right, I want to talk about your expectations, what you would learn from these 2 modules, hopefully, right? So by the end of, the 2 modules, hopefully we will get a good overview, right? We will not go into all the details of all the methods, but at least, we'll get a good landscape of the different statistical learning methods. So maybe in your future research, right, when you encounter some real world problems, you could think of, some of the methods we learned here that would be appropriate or, helpful to solving your research questions. And so we may not get a good chance, or a lot of time to do coding or programming in class, but I want to, introduce you to the relevant, for example, R packages or the R topics that can help you, carry out those analyses. So after class, right, if you are interested, or if you do have the need to use those methods, you would know what kind of R package you should use, right? And so in addition to, we introduce these different methods, I also want to emphasize on so scientific way, right? It may be kind of a general term, but a more specific term may be how can we try to solve the data science problems with a statistical solid, way, right? So how a statistician would think of solving these data science problems, or any data any data related problems, right? You want to analyze your type of data, and how would a statistician think? So that's the goal of these 2 modules as well. So at the end, right, I hope that you would be better equipped for your research or study or job, right? Gain something useful for your future study. So that's I want to say this is your expectations, but also my goals in order to introduce these methods to you. So as we see in the previous overview, the first module, right, we want to talk about predictive models. And so this high dimensional data has been arising, in a wide range of applications. As I mentioned, typically, I would say like the most typical example may be in genetics, right? So more or less people may have encountered, genetics data, and the typical data structure, right, from genetics or epigenetics is that we would have, if we consider your data as a data matrix, right? So this would be a data matrix, and oftentimes, the dimension of the data matrix is denoted by N and P, right? So N is your number of rows, P is your number of columns, right? That's a data matrix. So for example, in genetics, we would have, the subjects, right? Or the individuals that you take your genetic sample from. That would be your sample size, right? N. And then in terms of the columns, right, they could be your SNP or DNA related measures, right? And the number of SNPs or the number of genetic measures is the P, right? The column here. So the simple definition, right, of high dimensional data is essentially we have a very large P compared to, your sample size, for example, right? So in terms of the dimension of the data, we would have a much larger number of columns than a number of rows. So that's what we mean by high dimensional data. So this specific type of data structure, it has been existing, in research for probably decades of times, and people have, encountered numerous, challenges in analyzing this type of data. But at the same time, people try their best to develop, right, different statistical methods or techniques to better understand this kind of data structure. So, so basically, this is, the focus of our modules here. And because of this specific data structure, a key, goal when we analyze this type of data is model selection, right? Or another word is variable selection, right? So here, a variable, right, refers to, the columns in our data matrix, right? Based on the belief that, not all of these, for example, right, in a genetic data, we do not believe that all the SNPs are related to, our outcome of interest, right? So probably in addition to this data matrix, N by P, we could add the Y vector as well, right? Let's say we have the outcome vector. So this would be our outcome vector, for example, denoted by Y, right? Y1 through Yn, for example. So, so the hypothesis, right, or the assumption is that, not all of these P SNP variables, they are related to our outcome, right? So we want to find the actual, important SNPs, and that is a selection problem, right? So we want to select the relevant variables from the candidate, or, from all of the data that we have collected. So, so based on this goal, right, the goal of model selection, people have developed, different methods, and that is what we want to introduce. So in addition to model selection, we will talk about so-called resampling methods. And as I have mentioned, resampling is one of the fundamental statistical tools, right? So it is really like a very general, statistic. You can think of this as a trick, right? A statistical trick, but, we could achieve a lot, with this simple trick, or, this idea of resampling. And we will introduce, and really, like, for example, the cross-validation, bootstrap, these ideas, they are widely used when people are conducting statistical analysis. So they are it's a fundamental trick, but it is super, useful and in real world. So we will introduce cross-validation, bootstrap, and bagging as well, right? And and then, so the last topic, for the first module is so-called high-dimensional inference methods. And here, the word inference refers to, statistical inference, right? Statistical inference. And what we mean by statistical inference, I think, one good example that hopefully everyone here understand, or, you have encountered, is basically the p-value, right? I know there's a lot of, discussion on p-values, the pros and cons of p-values, right? But basically, you know, when you fit a model, you get your p-values. That is statistical inference, right? So what does the p-value tell us, right? So it is saying, you know, we estimate, right? So for example, oftentimes, or you know, in most cases, right, we would have the p-values for our beta hat, for example, right? That's, you know, the coefficient estimate from our model. So, or the effect estimates, right? So the p-values for our effects, right? So we get our effect estimates, right? But we, with only the effect estimates, we wouldn't know, you know, actually how important the effect is, right? It could be, you know, an effect of 1 or 2, but we do not have a comparison, or, you know, like a formal statistical testing, right? And the use of p-values is essentially to give your effect estimates an importance measure, right? So traditionally speaking, a significant p-value means that, you know, the effect is not 0, right? It's not 0 with a high probability, right? Or another way of saying is, you know, this effect is 0 with a small probability, right? So that is what we mean by statistical inference. Basically, you know, we want to give more definitive conclusions, right, to our effect estimates with confidence, right? So another word that we hear a lot is, you know, so-called confidence. So basically, whether we are confident, you know, in our effect estimates, that is measured by, you know, those statistical inference measures, and the p-value being one of, you know, maybe the most commonly used one, right? So that's the so that's the I want to, like, kind of the background, right, on statistical inference. And so coming back to this high dimensional inference, what we're going to talk about is, you know, with this high dimensional data, there are unique challenges for us to, you know, draw statistical inference that is different, right, from our low dimensional statistics. So we will talk more details later as well. Any questions so far? Okay. All right. So you know, to start with, like, before we jump into, you know, like the detailed statistical learning methods, we want to maybe first give some, you know, intuitive examples regarding machine learning in general, right? So so there have been, you know, machine learning is not a young field anymore, right? It has been advanced, you know, many decades. So there has been this debate, right, between, you know, which one is superior, right? Whether it's the machine produced results, or, you know, human based results. So one example here is that, you know, so by the way, right, this Andrew Nunn is one of the leading, you know, machine learning faculty. I believe his appointment may be still in Stanford, but he also works for you know, the big tech companies as well. Anyways, you know, he is one of the leading figures, right, in machine learning. And one of his quote is, you know, regarding the diagnostics, right? So the diagnosis from your chest X-ray, for example, right? So we know traditionally, you know, it is a doctor's job, right, to look at your X-rays, right, and to give the pneumonia diagnosis based on your chest X-rays, right? But actually, you know, with the development of machine learning algorithms, the machine could potentially do a better job, right, of the pneumonia diagnosis from the chest X-rays. So, so the question here is also, you know, how much we could trust the machine-based results, right? And the trust is, you know, another word of the confidence, right? How much confidence we have in this machine-generated results, and that is actually, you know, one of the questions both statisticians as well as computer scientists wanted to answer, right? You know, try to give, like, not only, you know, we want the machine to produce results, but also the trustworthy, right, of the results. So another example, right, that, you know, so for example, if you own a Tesla, right, you might be familiar with this topic. Tesla is, you know, devoted in developing this autopilot technique, which is largely based on machine learning algorithms, right? So in order for the machine, so the machine here is your car, right? In order for the machine to perform this autopilot task, essentially you want to let the machine understand what you know, its camera captures, right? So we know that, you know, for those vehicles designed for autopilot, there are, you know, multiple cameras on the vehicle, right? So basically, the cameras would capture, you know, the surrounding of your car, and so the raw image, right? The raw image is basically what's on the top panel, right? It's essentially you can think of as a picture or video, right? If you think of it as a continuous input, right, that would be a video. And so what is omitted here, right, is essentially, you know, through the machine learning algorithm, right, more specifically, right, this is a so-called image segmentation. Did I misspell this word? Sorry, let me, segmentation, right? Oh, yeah, with an E, sorry. Segment. So, yeah, so so this is called image segmentation, right? What and so there are, you know, a lot of algorithm developed for this specific task, and what it want to achieve is basically, you know, with the raw image input, we want to segment these images into different categories or different subjects, right? As the legend, you know, shows on the left, right? Basically, we want to, you know, separate the lanes, right? So, you know, the lanes are super important in autopilot, right? You do not want to, you know, misclassify one lane from another, right? That would cause a severe crash. So you want to separate the lanes from your, you know, surrounding environment. That is, you know, off-road, right? So there are off-road subjects, and so the road marks, right? So these, let me try to find the color. So these road marks, they are also very important, you know, in order for us to identify the correct lanes, and also, you know, other vehicles, right? So you also want to, you know, distinguish between moving vehicles versus parked vehicles, right? And another thing, you know, people the machine learning algorithm want to identify are the, traffic lights, right? So all these are, different subjects that we want the machine to, separate, in other words, to segment, right? And based on this image segmentation, it's essentially, one of the key steps towards fully autopilot, right? And but fundamentally, right, we can think of this image segmentation as a classification problem, right? And so maybe without the specific class labels, but we know that we want the machine to achieve certain types of classification, with the image input, right? So so the next example is so-called reinforcement learning, right? And it's also one of the major topics in the field, right? So different from like the previously we see people want to do diagnostics or people want to do classification. So here reinforcement means that the machine tries to accomplish certain tasks multiple times, right? So it is not a one-time task, but a key concept here is basically like the risk-reward idea, right? So so here we think of the agent or this robot, right? So the robot's task is to put out fire, for example, right? And this putting out fire is not a one-time task, but it may be going to different fires multiple times, right? So here we would define a reward for the machine, right? So if you successfully put out the fire, you would receive a positive reward, right? If you do not do a good job of putting out the fire, you would receive a negative reward. So over time, what we want the machine to learn is that it will find the better solutions, right, to achieve a higher reward or positive reward. So so that is a learning process over time, right? So at first, for example, here the machine do not know whether the robot, right, whether I directly go to the fire or I should get the bucket of water first, right? So this is like a binary decision for the robot, right? So at first, the machine do not know which choice it should make, right? So if the machine, and then we can think of this like the robot would make a random choice, right? So if the robot choose to go to the fire directly, right, then it would receive a so-called negative reward, right? Then basically the machine learn from this process, right? From this first iteration or this first encounter, the machine would know that choosing option 1, right, gives you a negative reward. And then the next time, right? So the key here is for reinforcement learning, you would perform this learning process repeatedly, right? So for the next time, even if the machine still randomly pick option 1 and 2, right? But sometimes it will pick by chance, right? It would pick option 2, right? Go to the bucket, get the water, and then go to the machine, right? So if the robot pick option 2 and then go to the fire, it may successfully put out the fire, right? So choosing option 2 would give you like a plus 100 reward, right? So that is a positive reward, and the machine would memorize, right, or record this positive reward. So then the machine would learn that option 2 is a better option than option 1, right? So through this, iteration of learning, and for this simple example, right, in future events, the robot would always pick option 2 instead of option 1 in order to, maximize its reward. And that's, the fundamental idea behind the reinforcement learning. And but however, I do not think we will go into like the details for this one. It is, it itself is a very large topic. Maybe, you can think of it as like a course of itself, right? So, but here we do want to, at least give the fundamental idea behind reinforcement learning. So, so to, summarize or, give a brief summary of the tasks of machine learning, right? When we talk about like different models or algorithms to solve problems, really there are, 2 different goals here, right? So the first task is so-called predictive power, meaning that, we want to use the input data information, right? And for prediction for the future values of output, right? So, we have certain, whether it is, classification goals or, classification problems or regression problems, right? Meaning that, we have continuous outcomes, right? The goal is to predict future values, right? And the performance can be, evaluated based on how accurate, right, your model can predict future values. So, so that is the first task, and then the second task. So the example here, right, is basically, we can think of the diagnostics example, right? Diagnosis, right? For doctors to make diagnosis, that's a typical, predictive task, right? And then the second task is so-called descriptive power, right? So whether our model, could find interesting human interpretable patterns that describe the data, right? Describe the data, or, we want to find important features from data. And the typical example, right, is, the autopilot example, right, where we basically want to do the segmentation, right? That is, to find important features, or, to do this feature segmentation, right, based on our image input. So, these goals, we want to separate them, right, as they are, very different goals. But most times, right, we try to find models that, works for towards both goals, right? We want the model to, have good predictive power, and sometimes, we want the model also to have a good descriptive power as well. So a few more examples, just for us to understand, like the tasks here, right? This is a typical, example if you follow some like sports events, right? Nowadays, during like the live broadcast, sometimes, it would provide this so-called like live winning probability, right? So this winning probability, changes as the game goes on, right? So so here the example here is, we see that the plot, right, shows below the box score is basically the probability, right? And as indicated by the blue curve, right? So the blue curve is basically like the probability of UCLA, right, winning the game, right? And then the orange curve, right, is let me check. Oh. Yeah, so the orange curve is the probability of Alabama winning the game, right? And immediately, we see that the summation of these two probabilities equal to 1, right? They are either one team gonna win the game, and we also see the the change, right? How these probabilities change when the game goes on. So this is essentially like a live prediction problem, right? Based on the history, or like the current score of the game, and also maybe the history between the two teams, or their individual previous records, right? So on and so forth, right? All those information, right? They are the predictors, or the so-called features, for us to make this probability, or to make this prediction. So that's like we want to produce this prediction in a timely manner, right? In the sense that it's updated throughout the game. And yeah, also, by the way, right, we can think of this probability as a continuous probability that we want to predict, right? So it is a continuous variable, or a continuous response variable that is between 0 and 1, right? It is, between 0 and 1. And then for classification, this is a really classic machine learning task that people have been working on for a long time. So essentially, there is like a public database, like public image database, that recorded I want to say like tens of thousands of images of these different categories, right? So let me try. Yeah, I think there's a name of I remember there's a name. Yeah, what's the name for this? ImageNet, is it the? Oh yeah. So this it's the so-called, I believe it should be this one, CIFAR 10. It's like really one of the oldest machine learning database. So here CIFAR 10, right? 10 refers to these 10 different categories of images, right? So they have have a wide range, from airplane, automobile, to different animals, right? And so the goal here is, with this public database, people can try their various machine learning algorithms to, perform this classification task, right? That's saying, based on your training set, right? And you develop your algorithm, then for any future images, right? So here, if we do have a future image, right, that is outside of this training set, then whether your algorithm could correctly classify the future image, right, into the corresponding category. right? That's the goal here. So that's a public data set, for classification. And quickly, right, another example is this so-called the digital classification problem, right? That is also a famous study, basically, actually, people collect these handwritten digits, right? They are all handwritten digits, and they are actually the zip codes from, the zip codes on the envelope, right? Zip codes on the envelope. So, we get all these different kinds of handwritten digits from different people as well, right? And this is a classification problem, in order for the algorithm to understand or to classify all the digits, right, into 0, 1, 2, all the way to 9. And that's another example. So the recommender system, right, is really, everyone here, I think, we encounter daily with this example. And this is another example of reinforcement learning. Because here, right, so essentially, whether, it is Netflix or YouTube or, even TikTok, right? So all of these platforms, their uttermost important goal is to recommend something, right? Recommend the content that you will, keep watching, or, that is suits your interests, right? So here, the recommendation is a repeated task, right? As long as you are using the app, it continuously gives you recommendations based on your history, right? Your viewing history, and maybe try to find similar patterns, right, between their users, right? For example, whether your viewing history is similar to someone else, and they could, recommend that similar person's interest, right, into your feed as well. And as I mentioned, right, it is a repeated task. People try to, the platforms, right, will try to give you different recommendations through this reinforcement learning task, right? So I believe this would be, the last example, and it is actually what I have been working on in the past a year or so. So this is another, disease diagnosis example, and we could go into some more details here, right? So so this is a collaboration. Just want to acknowledge my colleagues here from the UCLA Stein Eye Institute, right? So here, what we really look at is the so-called glaucoma diagnosis, right? We know that glaucoma is a very common eye disease, and it could, progress and cause blindness, right, to the patients. It is, a very severe eye disease as well. So here we want to give this diagnosis, or actually a classification, right, to the glaucoma patients based on their, so-called the disc images, right, or optic disc images. So so here the classification has essentially 10 stages, right? We have the so-called the disc damage likelihood scale. So it is from 1 to 10, and based on there are like two dimensions in order for us to do this diagnosis. One is the size of your disc, right? If you could read from here, whether it's small disc or average size disc or large disc, right? So we need to determine whether because people's disc size vary, right? So whether the patient's disc size is small, medium, or large, then based on the size, we will look at the so-called narrowest width, right? So this narrow width, in other words, is the rim to disc ratio. So that is a value or a measure that we calculate, right? So this rim to disc ratio, if it is essentially the smaller the ratio is, the more severe your glaucoma is, right? And that is what we want to learn from patients' optic disc images. So here's the illustration of what our method does, right? So on the left hand side, the left three panels, right? There are three examples of the raw optic disc image, and on the right hand side is what like our algorithm produce at the end, right? So so essentially, it achieves several things here. The first thing is that we want to do this. Actually, it's an image segmentation task, right? So we want to identify the two circles, right? So this outside circle is the so-called optic disc, right? So that's the disc. We want the machine to learn, right? Based on the image input, we want to identify the disc area, right? And the more, the brighter inside, right, is the so-called rim, right? So in other words, we want to segment this image into disc and the rim, right? So we want to, identify this rim area for subsequent analysis, right? So after this image segmentation, if we remember from the DDLS definition, right? The DDLS definition needs to calculate the rim to disc ratio, which is indicated on the right hand side, right? So that is the ratio between this segment here, right, versus the whole line, right, the whole the white line, right? So basically, it's the ratio of the shorter segment divided by the longer segment. That's what we call the rim to disc ratio, right? So clearly, we see that the rim segmentation is the first step, and then we want to calculate this rim to disc ratio, right, by identifying the narrowest rim, the narrowest rim on this rim, right, and then calculate the ratio. Then, in addition, right, we need to do this disc size prediction, right, as indicated here, right, whether overall your optic disc is large, medium, or small, right? That's another information we need. So by combining, we combine these two, right? The RDR ratio and the disc size prediction. We are able to do the DDLS grading at the end. So that's the task we want to accomplish here. So from this example, we see that, so this is, like a combination of classification as well as regression, right, for continuous measures, because here the RDR rim to disc ratio is essentially a continuous measure that we are interested in, right? And the disk size prediction, it's a typical classification problem. So my point is that, in real world problems, it is never like a simple task of, fitting a classification model, but combination of, all the tools that you have, right, in order to achieve real world, tasks. Okay, so hopefully, these examples give everyone a good sense of all the different machine learning tasks, or like the commonly seen one, right, in your daily life. And yeah, I do want to pause for, any questions that you might have. Okay, so let's move on here. This is, one summarize of the previous examples we have seen, right? So generally speaking, there are three types of machine learning problem. There are three basic types. So supervised learning, meaning that, we would have label data, right? In other words, we know the output of interest, right? So for example, here the disk size, right? These are the labels that we have for our disk images, right? We know, we want to know, the whether the size is small, medium, or large, right? So that means label data. And with label data, there are two types, like subcategories: regression or classification. We have mentioned this, right? For regression, that means continuous outcome, and for classification, that means you have the categorical, or the class labels, right? And the second type of learning problems is so-called unsupervised learning. So unsupervised learning, on the other hand, means it's unlabeled data, right? That is, the typical example of image segmentation, right? So when you do segmentation, you do not know exactly, or you do not know beforehand, right? What potential parts of the image you would have, right? But through the unsupervised learning process, you cluster, right? So you cluster the image into different parts that gives you different clusters, right? So so that's the fundamental difference, whether we have labeled data or unlabeled data. And the third category, we have also seen, right, is that so-called reinforcement learning. And the goal here is, basically to take actions, right? And it's, in order to maximize some notion of cumulative rewards, as we have also seen, right? So basically for reinforcement learning, you need to define your rewards first, right? You need to let the machine know, like, what is the reward, right? In what cases you would have, positive reward, what cases you may have negative rewards, right? After you define the rewards, you would train your machine to take actions, right? That's so-called reinforcement learning. So, less commonly used, right? There's also semi-supervised learning, but essentially it's, you can think of as combination of supervised and unsupervised. But, these three are the three fundamental types, right? So a few more details, right? We want to introduce some names or notations for future reference, right? So with supervised learning, you know, we could call, you know, the labeled data, right? The labels as output, right? So output means, you know, the variables we want to predict or we want to classify, for example, right? These are the outputs. And then another name is, you know, we call the outputs dependent variables, meaning that, you know, they depend on the inputs, right? So they depend on the other variables that you have. So the input variables, right? Meaning that, can we use? So the input variables, right? Meaning that we would use these input variables to predict output variables, right? So the relationship is like this, right? We use the input variables to, you know, predict the output variables, and so they are also called, you know, independent variables, meaning that they are generated or observed independent of the output, right? So that's just some names we want to clarify. And then for unsupervised learning, you know, essentially we have only the input variables, right? So that's what we mean by, you know, unlabeled data, that we do not have the output variables. Okay, so here's, you know, another example comparing these two tasks, right? So we clearly see that, you know, so we have these observations, right? Whether they are, you know, circles or crosses. But here, if we distinguish, right? If we distinguish, you know, circle versus cross, then these data points, they are labeled, right? They have different labels, right? The two different labels, circle or cross. And, you know, whether a data point is a circle or a cross depends on, you know, your input values, x1 or x2, right? So here, x1 and x2 are the input variables, right? So input x1, input x2, right? So we could see that, you know, essentially with smaller, right? Because, you know, as the axis indicate, right, this is the zero, you know, the origin, right? So with smaller x1 and x2 values, we would have, you know, our output to be a circle, right? So the output is, you know, circle versus cross, right? And then with larger, you know, x1, x2 values, we see that, you know, the output would be cross, right? And this is a really, you know, simple example that the two labels are clearly separated, right? And on the other hand, you know, for unsupervised learning, essentially we have only the inputs, right? We have the inputs of x1 and x2, and we do not have, you know, the labels are not distinguished, right? We do not know there are two potential classes, but what the unsupervised learning wants to achieve here is so-called clustering, right? So with clustering, meaning that, you know, when we are given these inputs x1 and x2, the algorithm want to, you know, separate the two classes, right? So potentially we learn from the input data that, you know, these two classes, they are distinguished, right? They are different, right? Even though, you know, we do not know their class labels, after clustering, right? We could give them, you know, like label 1 and the label 2, right? We know, you know, the labels are arbitrary, right? If we could do the clustering, you know, we believe the two clusters are very different, then we could assign different labels to them. Okay. Yeah, so is this clear? Any questions regarding the difference between supervised versus unsupervised? Okay. So now we will introduce, maybe more rigorous notations, because, at the end, we will be, introduce statistical models, right? So in order for us to, introduce the models, let's give some notations. So here we basically, denote, right, the relationship, the relationship between our input and output by the function f, right? So the function f, characterize the relationship between, so here we call the features x, right? The features x, in other words, they are, the inputs, and for the outcome y, that is the output, right? So, given input x through the function f, right, we could get our, output y. So f is the function we want to estimate or learn. So here we also, basically denote the x, right, from p-dimensional space, or RP, right, meaning that, we have p different features or inputs, right? So in this previous example, right, we have x1, x2. So here p equals to 2, right? We have 2 inputs, but more generally, right, we could have, x1, x2 all the way through xp, right? That this would be our x, for example. So for regression, essentially, we have the f function that is from rp to r, right? In other words, y is a continuous variable, right? Takes values in, any real numbers. And then for classification, right, y would be, a set, right? Or elements in a set C. So, the set C should be discrete, right? In other words, for example, for binary classification, right, you could have the set C as either 0 or 1, right? And in our previous the glaucoma example, right, for DDLS scale, right, we have the C, C has 10 different scales, right? So they are still discrete from 1 to 10. So that's, the notation for if we have, both input and output. Then for unsupervised learning, right? So we have, just a set of features, x, and we do not have y, right? And another notation, right, that is we want to introduce is so-called training data, right? So by training data, we mean that, we would develop or, fit our model on this training data, right? And here n denotes the sample size n of the training data, meaning that, we have samples, right, xi from, I equal to 1 to n. So that is, the samples we have. Each xi is a random draw of x. So here x is, the previous random vector x that we specify. So typically, right, xi, they are just IID copies, right? So we call this independently and identically distributed, right? IID copies of the input x variable or vector, right? So, the training data is one notation we want to keep in mind. And yeah, so for the later part, we will, learn more detail if we go into the supervised learning topic, right? So here is what we have covered, right? We have mentioned, the inputs or features, they are p-dimensional, and we denote the training data as D of n, right, with sample size n. And because, if we focus on supervised learning, we would have, both x and y, right? So both x and y. So y would take, different values for regression or for classification. Right. Okay. So hopefully, we are clear about the notations introduced here. So next, right, we will go over a classic, one of the oldest maybe machine learning algorithms that is called, the k nearest neighbor algorithm. So k nearest neighbor also, denoted as KNN for short, right? It is a non-parametric supervised machine learning algorithm, right? So the keywords here are, it is non-parametric and it is supervised, right? Meaning that we have label data. Can be used to solve, both classification and regression problems. The idea of, KNN algorithm is really simple. Essentially, we want to give the prediction only based on the neighborhood, right, of an input, right? So given any input, we want to use the neighborhood of the input to do prediction, right? And it totally makes sense as, an intuitive way to do the prediction, right? In real life, for example, one example maybe, if you want to predict the weight, right? So you want to predict the weight of a person, right? And the height, right? Say the height of the person. Then you want to find other people, right? That's, for example, similar in height, right? So for example, you want to find a bunch of people that are similar in height to the person you want to, find out the weight. Then you could, use the average weights, right? The average weights of those similar people to predict the weight of the person you are interested in. And that is, the idea of k nearest neighbor, right? And here k basically refers to, how many similar subjects do you use, right? Whether you find, 10 people that's similar in height, or you find 5 people, then k would be 5, right? So that's, really the intuition behind the k nearest neighbor. And to write out this intuition, right, into formula, we have the formula here. So we see here, the x, right, is the input that we want to predict. So we call this the target point x, right? In other words, we know that our target y, right, it is, this f function of x, right? But we do not know f. Right? For example, the relationship between your height and weight, right? We do not know that f. So that's the target, right? So in order to predict this y based on your target point x, we want to find, these xi's, right? So here xi meaning that, the xi's in our training data, right? We have the training data dn. So, and then nk defines the k samples from the training data, right, that are closest to x. So that's the neighborhood that we define, right? So, you know, we will, so if we think of the height as X, right? So basically, we want to find the people that's most similar in height to our target X, right? And K samples, right? So meaning that, you know, K neighbors. So for all these Xi that's in our neighborhood, right? They have the corresponding yi value that we observe, right? Because, you know, they are in the training set. So we observe their Xi and Yi, right? Then we simply take, you know, the average, right? So here the average of Yi's that is, you know, of this neighbor to get our Y hat estimate, right? So this Y hat is the, you know, estimate as well as, you know, it is the prediction, right? For our target X. So that's, you know, how we would write out the K nearest neighbor algorithm in a really, you know, a simple, just one formula, right? And on the other hand, right, for classification, you know, we could carry out this idea in a similar way, right? So, but, you know, instead of using all the YIs, remember here, you know, the YIs becomes the labels, right? So for the labels, we identify, you know, the same neighborhood first, right? So NK is, you know, the same neighborhood, but now your YI taking different values in your classes, right? Capital C. So capital C is, you know, like all the classes you have. And we want to find that the small c, right, the little c, that is most prevalent in the neighborhood, right? So for example, say you have, you know, two class labels, 0 and 1, right? And in your neighborhood, say nk of x, right? You observe, you know, 2 zeros and 3 ones, right? These are the yi values, right, in the neighborhood. So here, you know, your k is 5, right, basically. So for your k equal to 5, you know, in the neighborhood, you observe 3 ones and 2 zeros, right? So the most prevalent class in this case would be 1, right? So your what we get from, you know, this k nearest neighbor is that our y hat label should be 1, right? So so that's, you know, how we would perform k nearest neighbor for classification. So based on this definition, right? So this is, you know, so this is essentially all of the k nearest neighbor algorithm that we want to describe, right? So let's try to, you know, apply this k nearest neighbor to some simulated data, right? That's some data that we want to model. So we simulate this, you know, data of x and y, right, based on this relationship. So here, the 2 times sine of x, right? This function is basically the f of x function that's, you know, describes the relationship between x and y. And we have, you know, only one feature, right? So a single x in this case. And then, you know, to mimic real data, right, we want to add some random noise as well, right? So here epsilon is standard normal error, you know, that is a random noise that we add to our observation. So, so for example, on the left panel here, right, that is the simulated data that we observe. In other words, you know, this is the training data of x and y, right? So the horizontal axis, right, corresponding to the different x values from 0 to 6, for example, right? And then the vertical axis corresponding to the y values. It also scatters around, right? So the circles, they are the observed, data points, right? For example, we can think of them as data point D1 with, the X1, Y1 values, right? That's the first data point, and so on and so forth. And also, the blue curve, right, is the truth of, the 2 times sine of x, right? The blue curve is the true function. And we see, because of the random error, right, the observed data points, they scatter around the truth, right? Then, we start with this one nearest neighbor, right? So by one nearest neighbor, meaning that, k equal to 1, right? So we always, only using a single, right, closest data point to predict our y, right? In other words, to estimate our y. And we see this, very unsmooth, right? So it's essentially like a step function, right? This orange step function is basically our y hat. That is, or in other, maybe another notation, we could write it as f hat, right? So this is f hat function that we, fitted based on a one nearest neighbor, right? So for example, we see here, let's say we have a observation here, right? So this may be, the input x, right, that we have. So to predict, the y value for this input x, right, we find the one nearest neighbor, right, the blue circle here, that is closest to, our target x, and we use the value of this xi, right, the value of this xi. So, it would be the take the same value of y, right, the horizontal line, to predict this target x, the y value of this target x. So I do not think, we are satisfied with this one nearest neighbor prediction, because, it is, like up and down, it's a step function, right? And for example, compare this orange curve to the true blue curve, right? We see, discrepancy in certain values of x, right? So that is why we want to, we will consider basically different k value later. But yeah, I'm told, we should have a break, right, in the middle. So let's take, 10-minute break. We'll come back at 12:42, if that sounds good.
Yeah, that's fine. So let's take 10 minutes break and then reconvene at 12:42.
Yes, sounds good. Thanks.
Mm. Mm.
Okay, hello everyone. So I'm back. Yeah, we can get started, continue. I do see, a very interesting question in the chat. So, so the question is, how can these methods be applied to measure changes in handwriting with time or illness to prevent fraud, right? Yeah, I think it's a very good question, so basically, it is first of all, it is a different problem than, if we want to just classify the handwritten digits, for example, right? And I also want to say, it is maybe a more difficult problem than a typical classification problem. So from my knowledge, I do believe, one related a method is so-called variational autoencoder. And in other words, or it's so it is the yeah, I can just write it here. So so the method is called autoencoder. I think it might be relevant, yeah, just, from my experience. So autoencoder is a type of machine learning methods, right? That basically, considers like the or model the variation in your data, right? So to your question is, you are thinking of the variation. So the changes in handwriting, right? In other words, there are a variation in one person's handwriting, whether it's due to time or illness, right? So people use this idea of autoencoder that, let the machine learn this, or try to actually let the machine predict this kind of variation. For example, right? So you have your, input data of different people's handwriting, right? So handwriting from 100 different people. And what the machine tries to learn is that, take the input and try to output some similar handwriting, right, of the different people. So for person one, right, you have person one's input handwriting, and the machine would try to output the handwriting that is similar to patient one's, and so I think that may be, most relevant to your problem or your question. And, there are different variations of this autoencoder method. Yeah, if you are interested, you could maybe do some Google search or yeah, look into this. Yeah, but I do want to say, this one of the more advanced machine learning methods, but it's, useful in certain contexts, right? So there is another question. When using EHR data, more likely to use supervised learning, or can unsupervised learning be applicable? So yeah, EHR data, it is a very general, large topic. Really, I think to, choose between supervised or unsupervised depends on what data you have and what questions you want to answer, right? So for example, with EHR data, and you are interested, in some patient's characteristic as your outcome, right? For example, you want to, predict patient's illness or their disease progression or some other, quantity of interest that you predetermined, right? So with the predetermined measures of interest, that would be supervised learning, right? You take the input you have from EHR data, and then you try to, predict certain measures of outcome, right, or outcome of interest. And on the other hand, one thing, people have been doing, for example, is the so-called natural language processing, right, NLP. So we know that sometimes, right, for the EHR data, we would have, doctor's notes, right, on doctor's notes. So those doctor's notes, they are, like free text, right? And when, your EHR data is of large scale, right? Maybe you have hundreds of thousands of patients, you have a large amount of, doctor's notes. And if you want to learn, right, certain patterns, or, you want to extract, important information, right? Extract information, from these doctor's notes. I would say this is more like an unsupervised learning problem without, a specific outcome of interest, right? So you would simply, so you would have only the input data, right? Your inputs are doctor's notes in the EHR data. You want to learn, what kind of information you can get from these free text. That would be a unsupervised learning problem. Does that answer your question? Both questions, if you have any follow-up comments. Okay, so if not, yeah, let's continue with the K nearest neighbor example. So we just illustrated, right, the 1 nearest neighbor for our simulated data. So to write this out, basically we could, for this 1 nearest neighbor, we can write out the expectation, right, for f hat. That is, our 1 nearest neighbor estimate. So this is quite mathematical. We do not need to go over like all of this in detail, but essentially what we want to learn from here is that using 1 nearest neighbor, right, we see that the expectation of f hat is essentially the truth, right? We know that 2 sine of x is the true relationship f, right, the target. So in other words, it is unbiased, right? So we learn that, 1 nearest neighbor gives us unbiased results. However, if we calculate the variance, right, the variance is large because the estimator only use one observation at a time, right? So if we calculate the variance, we get the variance equal to sigma square, which is the variance of the error term, right? The epsilon, that we assume here, equal to the variance of epsilon. So the takeaway here is that 1 nearest neighbor gives unbiased estimates, but with a large variance, right? So do we like this result? Whether we could improve the estimate, maybe using a different K, right? So if we use more neighboring points, right? Intuitively speaking, use more neighboring points may improve the results. And more rigorously, right, we can show that the variance would reduce to sigma squared divided by K. So, for an estimate with smaller variance means, the estimate is more efficient, right? We would prefer the smaller variance in some sense. But at the same time, the bias will increase because as the neighborhood expand, right, your the neighborhoods you use to estimate the target, they are further away from the target, right? So it would introduce, additional bias. So this is essentially, the so-called bias variance trade-off, right? I believe some of you, must have heard this trade-off. So even in this, k nearest neighbor example, we want to illustrate this bias variance trade-off as well, right? So let's, take a more detailed look into this bias variance trade-off. So now instead of, just like a couple or a dozen of observations, we want to simulate 200 observations here, right? So n equal to 200. So the same, x and y, right, following the same truth as before, but now we just have more data points. And so once again, if we perform the one nearest neighbor regression, we see the fit, right? So the orange line corresponding to the fit of f hat, right? It is not desired in the sense that it really, jumps up and down with large variation that we could see, right? So it has a large variation, even though, it may be unbiased, it is not efficient, right? So compare this one nearest neighbor to say, 2 nearest neighbor or k nearest 10 nearest neighbor, right? So here k equal to 2 or k equal to 10. So we see that as we increase k, from 1 to 2, the variance is largely reduced, right? Because the variance is essentially indicated by the range of your fit, right? This range of your fit, indicates the variance, and when k equal to 2, this variance is reduced, and it is further reduced if we use k equal to 10 on the right hand side, right? And we also see that for k equal to 10, our f hat now is pretty close to the truth, right? When we look at f hat, compared to the true f indicated by the blue curve, they are it pretty much follows the blue curve, but with that is more wiggly, or there's more up and down, right? But we clearly see it is also improvement from k equal to 2, right? So if we further smooth our estimate, right? So we clearly see that the model becomes smoother as k increases, right? However, it eventually becomes biased in the sense that we see here. On the left, right, we have k equal to 33. That is, so basically later we will see whether we could find an optimal k, right, in some sense. And on the right, we have, k that is really large, right, k equal to 100. Keep in mind here, our total sample size n is 200, right? So k equal to 100, meaning that we would use, half of the sample every time, right? When we, as we estimate a single data point, right? So on the right-hand side, right, we see that with k equal to 100, there's substantial bias at many places, right? For these, x values, the bias becomes intolerable, right, in some sense. And for comparison, right, for k equal to 33, we do see that, the bias may be only problematic at the boundary, right? So that is also, one property or one limitation for k nearest neighbor, that its performance at the boundaries may be also less than ideal compared to the mid-range, right? The range in the middle. But for the middle range x values, the k equal to 33 case performs quite well, right? We could also compare k equal to 33 versus k equal to 10, and we see that this case is a smoother, right? The smoother f hat. So to summarize here, we see that let's see. So in this case, k is inversely associated with the model complexity. How do we think of this, right? So it's basically for example, if we have k equal to 200, right, the extreme case, then we would use all of the data points at all the times, right? Essentially, we would have a single f hat fit that is the average of all your so for k equal to 200, your y hat would simply be all the x, right, that you observe, take the average, right, divided by 200. So so that would corresponding to the simplest model, right? You have only a single mean as your prediction. So so from this we see that for smaller k, right, it's a more complex model, and for larger k, it's a simpler model in the KN case, right? So what this plot shows is essentially the prediction error, right? So by prediction error we mean when we compare the y hat versus the true y, right? And for example, we take the mean squared error, for it to be positive, right? So this is one definition of the prediction error, but basically we look at the difference between y hat and your true y, right? And we want to minimize the prediction error. So there are several curves here, and we want to go over them one by one, right? So first, the orange curve corresponding to the training samples, right, as indicated here. So what we see is that as we increase model complexity, the prediction error always goes up for the training sample, and that is what we have seen actually earlier as well, right? For k equal to 1, essentially you have the lowest prediction error on training sample, right? But on the other hand, of more importance, or we are more interested in the prediction error on the testing sample, right? So by testing sample, meaning that we take the x values, right, that's not in our training data, right? So for example, when we have less samples, this red x, right, this red x is a testing sample, right? It is not in our training data. So it would be an unbiased evaluation of your prediction error, right? So that's why we care more about the testing error prediction, testing sample prediction error, as indicated by the red curve. So in most examples, right, we want to observe this so-called U shape of the testing prediction error. So by U shape, meaning that we see the prediction error decreases first, right? And as the model complexity increases, and then it would, achieve some sort of minimum and then increase again as your model complexity becomes higher, right? So we want to observe this so-called U-shape, basically in order for us to find the best model, right? As indicated by, this purple vertical line, right? So the best model, in some sense, it basically minimizes this testing error, right? So that, it achieves the optimal in some sense. And so we would call, the models that's to the left or to the left of the optimal, right? We call them overfitting, and then call the models, that is like too simple, right? Call them underfitting, right? So, but that's just some names that we introduce. The point here is that by looking at the testing error, right, we could find the optimal model that minimize this testing error. So for example, in this simulated data, right, we do get the optimal K may corresponding to something like 30 something, right? And that is what we choose here, K equal to 33, like corresponding to our optimal model here. So the last thing we want to clarify from this plot is the bias variance trade-off, right? So generally speaking, to the left, right, indicated by this arrow to the left, these are more complicated models, so that they would achieve lower bias but higher variance, right? And to the right, right, we see for simpler models, they would achieve higher bias but lower variance, and that is what we call bias variance trade-off, right? So I want to say this is a very important plot in machine learning context, right? Because we will also talk more later, but in machine learning, we want to first distinguish your training and testing, right? And so we would always, expect the performance on training to be better as the model gets, more complex, right? So the performance on training indicated by this orange curve. However, right, we are more interested in the performance on testing as indicated by the red curve, right? So this red curve is basically to evaluate the model performance and for us to pick an optimal model. And in this case, right, we basically pick K for the K nearest neighbor algorithm. Any questions? Okay, so we go over the what is the true model, right? So that's a good point, right? So so essentially, we think of this prediction error, and so for the true model, we would know that this prediction error actually equals to let me maybe just write it here. So this is the blue curve, right? The blue curve, the prediction error is essentially the sigma square. That is the variance of our error term, right? We know that because this error of epsilon, right, that we added to the model. So we cannot model the error, right? In other words, so this variance of the error would always be in the model, and So sigma square is basically the variance we would get, right, even if we use the true model. So, and actually, you know, this scale of the prediction error here is essentially, you know, the expectation with respect to the, you know, true error sigma square, right, or divided by sigma square. So that's why we see, you know, it corresponding to 1, right? So for the true model, you know, the ratio is 1. So that's like a reference line, right? So that's also why, you know, the testing error, right? The red curve is always above the blue line, because, you know, blue line is the optimal we would achieve with the true model. You know, that's like the lower bound, right? And so the testing error would be above the true error. And we know that, you know, if the orange curve, right, it even goes below the true model, that's why we call this overfitting, right? Because we know the sigma square is unavoidable, right, even with the true model. And then you know, you have like a complicated model on the training data with the orange curve below the blue line, so that's indicating overfitting. Yeah, that's a good point. We want to clarify, right? Okay, so to summarize, right, we see, you know, how the model complexity changes with the bias variance trade-off. And so overfitting happens when the model performs well on the training sample, but not on the testing sample, right? So we want to control complexity. That's, you know, one of the takeaways here, right? And so one way to measure complexity, right, is what we so-call the degrees of freedom. So I suppose, you know, many of you must have heard the degrees of freedom, right? So degrees of freedom basically measures the number of parameters in the model, right? So for k nearest neighbor, essentially the degrees of freedom is, you know, roughly n over k, right? So it's not exact, right? But it's an approximate, gives us a sense. So we see that, you know, as k increases, the degrees of freedom decreases, meaning, you know, it's a simpler model. Yeah, so that's, you know, we want to introduce degrees of freedom and to, you know, prevent overfitting or to control complexity. We will see this formula, you know, a lot in the later part as well. But I believe this is, you know, the first time we introduce this formula, right? So this idea is that, you know, we want to quantify, right? We want to quantify like the effect of model complexity, you know, in our model fitting. So one approach is to penalize this complexity, right? So this is a very, you know, general formula. By the way, you know, for this argmin notation, right? If you haven't seen this, it's basically saying, you know, we want to find this f function, right? This f function that minimize the later term, right? So argmin means, you know, find f that minimize the following expression, right? So so that's our, you know, solution to argmin, right? So the objective, right, is the summation of the loss of f plus, you know, a tuning parameter lambda times the complexity of f, right? So this is quite, you know, abstract, but to give you like an example, right? So the loss typically, you know, is basically, you know, our prediction error, right? You can think of the error, for example, you know, between our F and the truth, right? So yeah, I mean, we use the same notation here, but so the one example of the loss, right, is just like the mean square error. For example, you know, we fit in linear model, right? Mean square error is a type of loss, and the example for complexity, right, is simply, you know, the degrees of freedom that, you know, measures the complexity of F, right? So that's, you know, one example. And further, you know, for this lambda parameter, it basically controls, right, how much penalization we want to impose here, right? So larger lambda means, you know, we want to penalize more of the complexity, right? And, you know, for lambda equal to 0, that simply means we do not penalize the complexity at all, right? So, so that's, you know, the general formula we want to introduce. And so we will, you know, yeah, I suppose, you know, some of you might have heard like cross-validation, or, you know, have used the cross-validation in your research as well. So here we briefly, you know, review, right, what cross-validation means and why it is, you know, related to prevent overfitting, right? So let's, you know, take an example, right, to fix ideas. So the example is the tenfold cross-validation, right? So tenfold means that, you know, we want to first randomly split, you know, our whole data into 10 equal sized subsamples, as indicated here, right? We see, you know, fold 1, 2, 3, right? Say 10, right? That's, you know, we first split data into 10 folds. And the next step, right, is basically each time, right, we want to use 9 out of the 10 subsamples as training data, right? And calculate the testing error using the remaining one. So the key idea of cross-validation is that, you know, although we only have one data set, right, we want to create, you know, training versus testing, so that the testing error we calculate, it is, you know, unbiased, right? So that's what we mean by, you know, it is very important to separate training versus testing in machine learning context, because we know that, you know, the error we calculate on the training data, it is you know, not valid in some sense, right? So we always want to, you know, focus on the testing error. And in this case, right, we would left out. So every time, right, we left out a fold as the testing sample, and then use the remaining as the training sample to calculate unbiased testing error. So this testing error is unbiased. So, you know, we alternate through all the folds and then take the average, right, to be so that, you know, we get a robust estimate of the testing error, you know, using all of the folds that we have. So this is, you know, the basic procedure, right, for cross-validation. And the goal here is basically, you know, we want to measure unbiased testing error from a single data set that we have, right? So yeah, we will, you know, come to cross-validation in more detail later. So this is just, you know, a brief introduction. So remarks on the degrees of freedom. Basically, you know, degrees of freedom is one way to measure model complexity, right? And this example is essentially, what we see as n nearest neighbor, right? We use k equal to n, right? The total sample size, and we always, would have the yi hat simply equal to the sample mean, right? So in this case, the degrees of freedom is 1, right? And further, for linear regression, right? People, we should be familiar with linear regression. Say linear regression with p predictors, right? Then that's essentially saying you have p model parameters, so the degrees of freedom is p, right? And then for k nearest neighbor, it's n over k. And we will see more examples of degrees of freedom later as well. So here is a comparison, right, between k nearest neighbor and the linear regression we are most familiar with. So really, both methods, right, both models have the same goal, right? Both want to approximate the truth, this true f, right? That is the expectation of y given our input x, right? Given input x, we want to predict y, and that is the goal here. So as we are familiar with linear regression, it makes a structural assumption that f is linear, right? In other words, linear model specify f of x, right, takes this linear form, right? Sometimes people write it as x transpose beta if you have multiple x, right? X as a vector. So this linear form is the underlying assumption, right, for linear regressions. And the good thing, right, the advantage of assuming this linear structure is that it would have low variance, right? The number of parameters is fixed, right? In other words, that's the degrees of freedom. As long as your p is small, right? That means your model is simple. So as sample size n increases, right? Even if you have more samples, the complexity does not increase, right? So the variance of beta hat is to the order of p over n. So the variance actually reduce, right, as n increases. So that's the good thing for linear regression, right? It has a lower variance, but it could have a higher bias because linear assumption is very restrictive, meaning that it like the true effects, right? The true effects of your x may not be linear, so your fitted f hat may have the potential bias, right? So on the other hand, for k nearest neighbor makes no assumption on f, and that's actually what we saw at the beginning, right? That's why we call this non-parametric, meaning that we do not impose parametric structure, right, to the KNN model. So it is non-parametric, right? So it is more flexible. So in return, right, we have low bias, and it can be shown that as k increase, right, and k over n goes to 0. So that's relatively speaking, right? If your sample size increases and then your k increase with the sample size n, but at a slower rate, right? Then kn is consistent, meaning that it is unbiased, right? So the expectation of f hat equal to the true f. So that's what we mean by unbiased, right? However, it might have high variance, as we know, the number of parameters is roughly n over k, right? And from this condition, k over n goes to 0. That means n over k would go to infinity, right? So the model complexity increases, results in higher variance. So this is, another example of bias variance trade-off when we compare KN versus linear regression, right? So, so previously, we see the KN example for regression, right? Meaning that we have continuous outcome. Now we look at the KN example for classification. So, so this is a classification problem. As we see, there are two different class labels, right? For example, we denote blue circles as 0 and then orange circles as 1. And we have, two-dimensional input as well, right? So essentially the inputs are x1 and x2, corresponding to the values on the axis, right? For simplicity, right, we can just assume, the range of x1 and x2 is between 0 and 1, right? So let's see, do we have, so to write this out as, like the data, right? The data triplet, essentially we have, the triplet of x1, x2, and y, right? x1, x2 takes the values between 0 and 1, and then y takes the class label, right, of either 0 or 1. So this is the, data structure here. So first, intuitively, we could see some sort of separation, right, between blue and orange. So that means, potentially we could use x1 and x2 to predict the class label, right? If, the two colors are entirely, randomly mixed, then that means, x1 and x2 are not informative, right, for us to do the classification. So here's, just an illustration of a k nearest neighbor for classification. And it's, less data points, so it's clearer illustration, right? So, so this is, essentially like the majority voting idea, for k nearest neighbor, because, in this two-dimensional case, right, the neighborhood of any input x, right? So this, black dot is the input x, right? We could, define the neighborhood as a circle, right, center around x, and essentially, as you increase the radius of the circle, you would increase k, right? So there's a correspondence there. So so this circle, right, corresponding to a k equal to 3 case, and then we clearly see that the most prevalent class in this case is the blue class, right? So from this example, we would assign blue to this black dot of x, right? So it would be predicted as blue. So we would so we would predict this dot as blue, right, based on this 3 nearest neighbor. And so on the right-hand side is just, like the illustration of 1 nearest neighbor, right? We see that the prediction basically, segment the whole input space, right, into regions of blue or orange. So once again, right, so here, with 1 nearest neighbor, it is not smooth, right, in the sense that, the regions, they are do not have like a uniform pattern, right? It is very wiggly or zigzag that separates the whole input space. So coming back to our example, right? Here's maybe a better comparison, right? So if we fit this k nearest neighbor idea to the previous example, right? So on the left we have k equal to 1, and on the right we have k equal to 15. So clearly we see that for k equal to 1, the classification is not smooth, right? In other words, it has high variation, right? And the regions they are discontinuous, right? The regions are not connected in a certain sense. But as we increase k, we reduce the model complexity, so the classification becomes smoother, right? So this on the right, it is smoother with lower variance, right? But at the same time, right, it would introduce more misclassification, right? So by misclassification, they are essentially the blue dots that are in the orange region, right? So the orange region meaning we would predict all the input as orange, right, in this region, but these blue dots indicating misclassification. And same thing, right, as the orange dots or orange circles in the blue region, they are also misclassification. So as we further increase k, right, we would get we would get more smooth fit, right, with basically less complex model. And so here k equal to 66, and we compare this to a linear model, right, that uses only 3 parameters. So intuitively speaking, right, remember our data is y with x1 and x2. So the linear model we fit would be something like this, right? Beta 1 x1, let's say y hat, right? Just to use the fitted values. So this would be the linear fit that we fit. And it's also actually not ideal, right? We know that. So if some of you learn the generalized linear model, we know for binary y we would prefer like a logistic regression, for example, right? But in this case, just for illustration, we basically fit a linear model to this data, and so it has only 3 parameters, right? Beta 0, beta 1, and beta 2. And the fitted line would be something like this on the right, right? So even with k equal to 66, it is still more complex than the linear regression, right? And in this case, if we compare k equal to 66 versus the linear regression, we might prefer the linear regression as it is simpler, but potentially achieve similar prediction error, right? Because the 2 lines, or they are similar in some sense. But another comparison is potentially we could compare the k equal to 15 versus the linear regression, right? And that may be we might prefer k equal to 15 because potentially we would have less misclassification, and the data, right? The data might exhibit like a nonlinear bound. So we call this like the separating bound, right? So this bound, indeed, it should be nonlinear. And when we use this linear line for classification, you know, there is a lot more misclassification, right? Yeah. So to, you know, formally, you know, show this comparison, right? We come back to this same prediction error plot, right? We have seen earlier. So, so similar as before, you know, we have the training curve, right? So the training curve is the green one. So it is decreasing, right? As you know, your model gets more complex. So here we see the degrees of freedom, right? N over K as it increases, meaning, you know, it's more complex model, right? So the complexity increases as well. So the training error is, you know, monotone decreasing, but for the testing error, right, it has a U shape, meaning that, you know, we could pick, you know, like an optimal testing error, right? Something like this, or yeah, so something, you know, either here or here, right? Corresponding to the N over K. And I think, is it like our N should be 200? And yeah, anyways, so the point is, you know, based on this U shape of the testing error, right, we could pick the optimal model with, you know, like the best, with the best performance, right? And also, you know, this purple horizontal line of the Bayes error, that's, you know, essentially the reference line, or, you know, the truth, right? So once again, you know, we see that the testing error should be above the reference line. You know, you can never achieve the truth, right, basically. So in addition, right, we also, you know, marks the testing error from the linear model, right? So we do see, you know, the linear model is a rather simple model, right? Because, you know, it corresponds to like the degrees of freedom 3, right? It's a simple model, but the testing error, right, compared to the optimal ones, it is inferior, right? It is, you know, worse than the best KNN model. So that's the idea. So I think, yeah, that's pretty much, you know, we have introduced KNN, you know, that's like the first maybe machine learning algorithm we introduced in this class, right? And we get a sense of, you know, how to evaluate, right, this KNN model in terms of the model prediction and the trade-off between bias and variance. So to give also some additional remarks, right? For KNN, you know, we must compute and sort the entire training set for each future prediction. So meaning that, you know, computationally, right, it becomes more demanding as your N increases, right? So for large sample size, you know, KNN would be inefficient, right? And actually, one thing we did not go into detail is basically, you know, in order to define the neighborhood, right, we need to define the distance as well. So, so the distance is, you know, it's quite straightforward, you know, in our previous examples, but they may not be clear in, you know, like more complicated cases. So we need to define the distance in order to use k nearest neighbor. That's another, complexity of the method, right? And sometimes, with certain distance definition, computationally it may be expensive, right? Yeah, so the distance measure needs to be specified. That's pretty much, the summary for our k nearest neighbor algorithm. Any questions before we move on? Okay, good. So, so this is, basically like an introduction and one example of the method, right? So now we would move on to the linear model, right? So, so first, a quote from the ESL book, actually, right? So, understanding linear methods is essential, for understanding nonlinear ones, and it is quite apparent, right? We, generally speaking, we always want to start with something simpler, right? Easier to understand, and linear model is by far, much more widely used, than nonlinear models because of the simplicity, right, and interpretability as well. So we will start with, linear methods and specifically, linear models for regression, right? For classification, it's, some adaptation, right? We could use to change the model for classification. And so because, we would focus on the high dimensional cases, right? So for high dimensional data, we have mentioned, we need to find important features, right? Out of all the inputs that we have. So we will talk about, methods for variable selection and a specific, a very widely used concept as, the shrinkage concept, right? So so you can, think of this shrinkage idea is basically, this penalization idea, right? Penalization idea, where, we want to penalize the model complexity, right? As the, previous formula we have seen. So there are two, well-known examples in the shrinkage methods. One is the ridge regression, right? The other is lasso. So we will go into details of these methods as well. Okay. So first, right, we want to introduce some further notations. So this training data, D of n, we have seen before, right? But here, instead of a single xi, right, we want to, write xi as a p-dimensional vector. Right, so here xi is a p-dimensional vector. We can write out xi to be xi1 through xip. And, we have different names, right? But they all mean the same thing, whether you call them predictors, covariates, features, or inputs, but they all refer to this xi vector, in our training data. So, and then for yi, right, we consider yi to be the continuous case, right? So yi coming from, the real line, take the real values, it is a continuous response. And we also have different names for yi, right? Either call it the response or outcome or output, but they all mean the same thing. Okay. So, a bit more notation, right? We could write x into, a vector form or, the matrix form. So basically, what we write here is essentially we call this the design matrix, right? The design matrix X is n by p dimension, right? And X is essentially, X11, X12, all the way to X1p. Then the second observation, right? X2p, and all the way to the nth observation. Xn1, wait, why this? Oh, yeah, I must have clicked the bottom. So X11, Xn2, all the way to Xnp, right? So the rows, right? The rows we denoted by this xi, right? And then the columns we denoted by, this capital X, and we call this xj, right? In general. So each column is, xj for j from 1 to p, right? So we have, x1 through xp. That's just a notation for the design matrix X, right? And that is also, your inputs. Okay, so the goal here, right? The overarching goal here is, we want to estimate the function fx that's, related to y, right? And what we have, seen is basically, right? So the y is related to x through this f function. And so the point here is, right, the true f is unknown, right? And we want to estimate f. In other words, we want to give an f hat of x, right, to predict y. So normally, right, we would also write hat x as y hat. And so formally, we define a loss function L as, a measure of discrepancy between y and fx. Yes? Oh, okay. So, so essentially the loss, right, means the discrepancy between y and f of x. And, a commonly used loss function is so-called squared error loss. We have used a lot. That, we can write it as, y minus fx and squared, right? And because, our x and y are random, right? They are, random vectors or, random variables. So we could take the expectation here, right? So the expectation of the loss is called the risk, right? And by taking expectation, we mean, it becomes non-random, right? So so the loss is with respect to y and fx, but the risk, right, only with respect to f, right? So it taking into account the randomness of x and y. So yeah, that's just two definitions, right? The loss and the risk. Because we would never know the true risk or the true expectation, right? But we are only given the training data, right? So given the training data, we want to calculate the empirical risk. So meaning that we calculate this risk based on our n samples, right? So the average over n training samples that we plug in our yi and xi, right? These are our training data into the loss function, right? Then simply take the mean. So if the loss is the squared error loss, right? If we use a squared error loss, the formula, becomes the later one, and we could, remove 1 over n, right? Because 1 over n is, does not affect your f estimate, right? So we call this f hat, or our target is this f hat that minimize this empirical risk, right? So argmin is, the notation we have introduced, right? That minimize the objective function, and f hat is the minimizer. And here, how do we call this? Like this f, right? So this f is just a space of models that we consider. So for example, right, if we consider linear models, then this f means, all the linear model, or like all the linear combination of x that we consider, right? So it specifies, what models we would consider for f hat. Okay, so this is, the definition of empirical risk, right, that we want to. So here's the illustration, for example, right, what do we mean by minimizing the empirical risk? So here, essentially we have like x1 and x2, right, as our, inputs. They are, the plane, right? And then the vertical axis is essentially, the y, that is the output, right? So then all the, red dots, right, they are the observed data, right, or the training sample that we have. Given x1 and x2 value, we have the y value, right? So and we see, there may be some, random error as well, right? And so the so this curve, right, or the this, how do we call this, like this shape of curve, or this is essentially the f theta function, right, representing, this curvature plane, right? Yeah, let's call this, the curved plane corresponding to a certain f theta function, right? Then, so here we have the theta notation, meaning, theta is the model parameter that specifies f, right? So so basically we want to fit theta so that this f theta would, minimize the sum of square vertical errors, right? So here the vertical errors are exactly, the difference between our y and f theta, right? And we only need to, take the squared sum of these vertical errors, right? So just to take one example here, right? So, this vertical error, right, corresponding to the difference and between y and f theta of x, right? And we only need to, take the summation, take the squared, and then take the summation, right? Then that's the, empirical risk that we want to minimize. So, this is just one visualization, right? What do we mean by minimizing the empirical risk for a general f function? Now we, move on to the linear regression specification, right? So clearly we see, this curved plane, right? This is a general f function. But if we, restrict ourselves to linear regression, right? So we can write the relationship as y equal to x transpose beta plus, you know, the error term, right? So epsilon is the independent error term. So here, essentially, you know, we, yeah, so this is just the matrix form, right? We could have the y vector, right? Y is a vector, x is a design matrix, you know, we have seen earlier, and then beta, right? Beta is the coefficient vector. To write this out, right, would be beta 1 through beta p, you know, the p vector. And this is the matrix form, right? Yeah, some of you might have seen this, right? So then, you know, given this linear model specification, right, we can write out the squared error loss. That is, you know, what we have seen, right? So if we write out this residual sum of square, in other words, right, this is essentially the empirical risk, right, for our, you know, linear model. So this is empirical risk, which is essentially, you know, what we write as the yi minus f of c xi squared, right? And here we simply, you know, take this f of xi as xi transpose beta, right? In other words, you know, this is the summation here. Oh, this is not a comma, right? This is just a minus sign. And so, you know, so this residual sum of square is what we get, right, as the empirical risk for linear model or for linear regression. So, you know, in linear regression context, right, we call this ordinary least square estimator, right, for beta hat, which simply, you know, minimize this empirical risk, right? And to you know, to clarify, right, basically the empirical risk is a more general definition than this ordinary least square, right? So the ordinary least square is a special case when we consider, you know, linear regressions, and this should be, you know, familiar to most of us, right? So the illustration here is, you know, we see that for linear regression, right, because it is a linear function of x, so this plane becomes, you know, like there's no curvature, right, to this plane, and this is essentially, you know, the x transpose beta plane, right, of our f of x. In other words, you know, you can think of this as beta 0 plus beta 1 x1 plus beta 2 x2, right? That's what the plane, you know, indicates. And the residual sums of square, right? The RSS basically corresponds to, you know, the summation of all these squared error bars, right? If we take the summation of these squared error bars, we get the residual sum of square. And, you know, from this visualization, it should occur to us that, you know, to minimize residual sum of square makes sense, right? Okay. So this is, you know, if you have learned this, that is very good, right? If you haven't learned like how to estimate beta hat, it is okay as well, right? You know, because all of the programs we use now automatically gives you the beta hat estimate. Okay. Sorry, yeah, I see. Sorry about the baby crying. Do you want to mute yourself? Oh, actually, I can. Okay. Yeah. Yeah, we are almost, I think, at you know, the end of today's lecture, right? So let's try to, wrap up. Basically, we provide, the beta hat estimate and the y hat, right? So we could, write out our prediction or the fitted value, right? And with y hat, right, we also want to, define the residual vector, right? The residuals is simply, the actual y that so the difference, right, between the actual y we observe and the y hat that we fitted. So these are some, mathematical derivation, but, it's optional, right? So in addition, right, we could get our error variance estimate as well, right? This is, the estimate of the variance of epsilon, right? And another, visualization, right, of the vector space interpretation of the linear regression fit that we introduced, right? So once again, we consider x1 and x2, right, two inputs. So so for any, right, x1 and x2, we have the observed y, right? That is what's observed in our data. What linear regression does, right, is we project this y, right, into the column space of x1 and x2. So that is what we have here, the x beta hat, right, which is, y hat, right? So y hat is essentially this projection here, right? And, so y, so the difference, right, between y and y hat is epsilon hat, right? That's the residual. And we immediately see that, this residual is perpendicular to the column space of y, right? That is what we wrote here, orthogonal to, each column of x. So epsilon hat is, same as R, right? The residual here. So in other words, our x transpose times epsilon hat is 0, right? So that's equivalent. Yeah, so we could, stop here, but essentially we introduced, the linear regression and the ordinary least square estimates, right? We will, go into more details, essentially, right? How to deal with large P tomorrow. Okay.
So any questions for Dr. Z? Questions, comments?
Yeah, I'm not sure if it's a good sign or not, but either, everyone fully understands or no one understands it.
Maybe okay. they are tired. It's 3 hours. So okay, yeah, so we thank Dr. Z so much for a great overview of the fundamentals of this model. So sometimes it's good to know or understand the fundamentals so that once you have an output, then you are able to interpret it better. So we thank Dr. Z again, and then we'll meet same time tomorrow to continue with this presentation.
Okay, thanks everyone. Yeah, I'll see you tomorrow.
Thank you. Great material. Thanks a lot.
All right, thanks.